Back. You were surprised that I was back, weren't you? I'm back with my vitamin water, a different flavor. This flavor matches my shirt, doesn't it? Well, today what we want to do is learn about something called a colligative property. Now, a colligative property is a property that does not depend upon what is dissolved in a solution, we're talking about solutions, but how much is dissolved. And they're called colligative properties. We're going to focus on freezing point depression and boiling point elevation. So let's have at it now. All right, so what the heck is a colligative property? Got my pen, probably should change to a color. We need a black color. Podcast 9.6, colligative properties. There we go. So colligative, that's a kind of a big fancy word, isn't it? All right, let's kind of define this. What is a colligative property? A property that depends only on the amount of solute dissolved, not on what is dissolved. So it doesn't really matter how much, but how much is what matters, okay? There are a number of different, and actually here's a good picture. If we have a pure solvent, let's just say for the sake of example, this is water right here. This water then has solute particles dissolved, the brown particles. And notice here, what's going to happen is that there are more particles here that evaporate than here. Essentially, the reason the colligative property happens is that the solute particle, the brown particle, is attracted to the blue particle, so it is less likely to evaporate. It holds on to the substance more tightly from sort of a bonding perspective. Okay. Now, what we want to do is I want to show this to you. It's probably easier to show this to you. And so what I want to do is I want to do a demonstration. And so we're going to cut to that right now on the video screen. Okay, so what I've got here, folks, is I have two beakers. Beaker number 1 and beaker number 2. They're both filled with ice. All right? Ice, of course, is just water. And I have some probes that are hooked up, and we can kind of record the temperature. And you can see on the screen the temperatures are pretty close to 0 degrees, right? But I've also brought with me some salt. So here's the salt. I'm going to pour the salt into one of the beakers, and I want to see what happens to the freezing point as I add the salt. So here I'm going to pour salt into this particular one. I'll be like generous. Now I'm going to mix this all up. I lost one. Now you might have seen this. Where have you seen this happen before? Done this before? If you've ever made homemade ice cream with salt and water, all right. Now, as you can see on the screen, you can see that the temperature of the substance with the salt is negative 11 degrees. That's this one right here. This, of course, right here is still at 0 degrees because it is, well, why? Why do you think? Why is this one still at 0 degrees? Well, it's just the melting point of water, but now this one's at minus 711 or whatever the temperature is that you can see on the screen, and so that causes the temperature to be significantly lower. So this is one of the colligative properties, and it becomes more pronounced the more salt I add. So if I add more salt, it should get colder, hence that concern that it's a colligative property. It means it depends on what the concentration is. So this is called freezing point depression. I'm depressing the freezing point. Instead of the freezing point being 0, as in this picture, it is negative a bunch in this picture. It's still the same deal. Okay? We'll talk about it here in just a second. So we just did that demo, and so let's talk some more. So we did ice water, salty water. We could also do this with boiling water and boiling salt water, and something else would occur. All right, so there are essentially two things that can happen. If I were to have a more concentrated solution, so think of that salt water that I just had, then you would have a higher boiling point. So if I took that salt water and I boiled it, I would find a higher boiling point. And on freezing point, what you would find is the more concentrated a solution, what did we just see just a minute ago? That's right, the lower the freezing point. So that freezing point was like minus 11 or 12 degrees Celsius, depends on what the concentration was, where water normally freezes at 0 degrees Celsius. So the freezing point is lowered. You could kind of picture it this way. Think of it this way. If water is a liquid from 0 degrees to 100 degrees, of course this assumes sea level temperatures, or pressures, pardon me, if this is water right here, so copy this down. If you had a solution, it's going to be at a greater temperature range. It's going to freeze at a lower temperature and boil at a higher temperature, maybe 110 degrees, and maybe this is negative 20 degrees or something like that. There's actually math where you can predict how much it will go up and how much it will go down. But essentially, but we're not going to do that. Essentially, the key thing is that it can be a liquid for a longer period of time, which is very cool. I've already seen that. We've got all kinds of weird animations. Now, where have you used this? What are some applications? Hopefully you understand this is a picture of some antifreeze. What is the purpose of antifreeze in your car? Well, this is a liquid that's designed to cool down your engine. He's pouring it in the radiator of his car. And you want its substance to be liquid. If it were to freeze, if you put water in there, especially where we live at 8,500 feet, those of you who are watching this outside of our little town, it gets kind of cold. And so if it gets really cold, if you put water in your car, it would freeze. And of course, if it freezes, it expands and it would burst your radiator. On the other end, if you're at a very hot day, you also want the boiling point, because if water, this is 0 and 100, that's just water. But if I have a solution, then it can be from negative something to 100 and something, or maybe 200 and something. And you can increase the point at which the substance is a liquid. Because you see, if the liquid in your radiator boils, it'll turn to a gas and it will explode your radiator. And if it freezes, it will burst your radiator because the ice will expand and it froze. So what they do is they take this chemical called antifreeze, or ethylene glycol, they put it into the car engine, and actually it's water and ethylene glycol. It's a solution of the two, and it's very important. It's a very important application. And those of you who live in cold weather climates, we certainly do, is we oftentimes put salt on the roads. We just saw that illustrated just a minute ago. If you put salt on the roads, what does that do? Well, it melts the ice. You see, what's dangerous on your roads is ice, right? But if you take the ice and you melt it and you make it a temperature at minus 10 degrees Celsius or something like that, like we just did, and it would still be a liquid. If you drive your car on that, you're driving just on water. It happens to be water that's a solution. It can corrode your car and cause issues, but it's better than dying on the roads. So it's other important applications. And then I mentioned this, you've probably ever done a homemade ice cream. If you have homemade ice cream, out here what do you put? You put salt, don't you? You put salt and ice and you can lower the freezing point. All right. Now why does this property occur? All right, this is where we kind of alluded to it. The key is the attraction of the solute, the brown in this picture, for the solvent, the blue in the picture. And it holds onto it more tightly so it cannot evaporate. So why is the freezing point depressed and the boiling point elevated? All right, because what we have is we have interference of the solute with the solvent. And that, my friends, is it. It's just an interference. Or you might, instead of words interference, you might talk about it's actually more better to say the attraction of the solute for the solvent causes this to occur. And it causes two things to occur: the freezing point to be lower and the boiling point to be higher. There's actually two other ones. The vapor pressure is lowered and the osmotic pressure is lowered. But we're not going to worry about those two. The key things that you have to know is the freezing point is lower and the boiling point is higher.